Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In Gauss's study of sums of squares, he used his eponymous Gaussian integers to study this question. And one of the key tools that he used was the norm map. So in this video, I want to show what is the norm map in the general setting, where you're looking at not just sums of squares, but more interesting arithmetic questions. And also related to this is the question of what is a sensible set of integers when you allow more numbers involved? Can we generalize this set of Gaussian integers to other contexts? Okay, so let's start with the norm map here, and let's recall what happens in the case of the Gaussian integers. So in this case here, we can look at the field extension of Q, where you just adjoin I, the square root of -1. And what was the norm map? Basically, it was just the square modulus. Okay, it sends x plus iy to the product of x plus iy with its complex conjugate to give you x squared plus y squared. And this is the reason why this norm map is useful in studying sums of squares. Okay, because this is actually a multiplicative map. And this multiplicative map, the image of this gives you a sum of squares. Okay, so basically, if you want to write something as a sum of squares, integer squares, you basically want to factorize it like this inside the Gaussian integer zi. And one of the key things about this norm map is that this is on the level of fields. If you restrict this norm map just to the Gaussian integers, its values will be integral. Okay, they will spit out integers. So the question I want to have a look at is, well, how do you generalize this setup? Okay, so let's look at the more general setup. So rather than just looking at this particular field extension, we'll now have k over f is some finite field extension. Okay, and basically we want some multiplicative map which goes from k back down to the smaller field f. Okay, and that's kind of a universal way to do that. So in general, what's an easy way to get a multiplicative map? Well, the determinant is one such very, very good source. So we're going to use that. And how do we do that? Okay, so let's start with some alpha inside k here. And what we can do is we have a map on k which is just multiplication by alpha. So that means that it sends z to alpha times z. Okay, so that's a very nice map. And one of the things that we should notice about this map is that, well, actually it's k linear, but in particular it's f linear. Okay, so how are we going to define the norm map now? Okay, I'm going to define the norm map, which depends on this field extension. So sometimes you put in the subscript k over f, and it goes from k to f. And where does it send alpha? What you do is you look at this m alpha as a f linear map from k to k. And k, remember, is finite dimensional of f. And since it's a f linear map from k to k, and k is finite dimensional, you can talk about its determinant. So that's the definition. Okay, and since here you're looking at this as an f linear map, okay, this determinant here, of course, will have values inside f. Okay, so it does land inside f, so you go from k back down to f. And the other key thing is it's multiplicative, so let's just check that it preserves products. If you want to take the norm of alpha beta, so by definition, what you do is you look at the f linear map where you multiply by alpha beta, okay, and you take the determinant of that. But of course, if you want to multiply by the product alpha beta by associativity, it's just the same as multiplying first by beta and then by alpha. So this is just a composite of m alpha and m beta. So you take the determinant of this composite endomorphism, okay, composite of linear maps. And of course, well, the determinant is multiplicative. That's why we used it. So this is the determinant of m alpha, which is the norm of alpha, times the determinant of m beta, which is the norm of beta. And there you have your generalization of the norm map for any finite field extension. Now, I said to generalization, so I guess I should say that we recover the usual norm map in this case here when you look at the Gaussian rationals. So how does that work? Okay, so let's try to understand that in this particular example. So you have the norm here, where you have the Gaussian rationals over the rationals here. So this is a degree 2 extension where you join the square root of -1. Let's apply it to x plus iy. Okay, so we want to look at this multiplication by x plus iy as a q linear map. Okay, so we need to pick a basis for q of I over q. So let's pick the basis 1 and I. So the representing matrix, you just see where 1 goes to. When you multiply x plus iy with 1, you get x plus iy. So with respect to the basis 1 and I, it's going to be 1 x here rather. So let's just get x. X is here. X is here. And y is here. And then with the other basis vector I, you multiply I with this, okay, you'll get the real part will be I squared y, which is minus y. And the imaginary part will be I times x, so you're going to x here. Okay, so multiplication by x plus iy, if you want to think of it as a q-linear map, with respect to the basis 1i, it's represented by this matrix, and then you can take the determinant of this rational matrix. Okay, so it's just x times x squared minus y times minus y, so minus negative y squared, and that gives you precisely x squared plus y squared, which is the norm map that Gauss introduced. Okay, so this is wonderful that we recover the norm map that we had before. Okay, so that's rather nice. It's quite easy to generalize this notion of a norm. So the next question becomes, well, what does it mean to be an integer? Okay, so let's try to think about this question. Okay, so we're going to assume now, since we take our the rationals as our base and usual integers as a base, we'll start with that as the bottom field, and we think of some finite field extension k of that. So we're like in this situation here. Okay, and the question is, well, what's a sensible subring R of this big field, which we consider as the integers? And I don't want to go through the full answer for that in this video. Okay, I just want to motivate what is this notion of integrality. So the key thing, I guess, that we want is that the norm of this R is going to be inside this Z. Okay, it'll be integral. And the way I'll answer this, I don't want to give a precise proposition here. I'm just going to do a little thought experiment to motivate what is the correct definition. Okay, so we'll just look in a simple case so that the calculations are a little bit easier. So here, the calculations are easy. You have a 2 by 2 matrix because we've got a quadratic field extension. So let's just suppose that K is a quadratic field extension of Q. So the degree K over Q is 2. And we consider some alpha that we want to be integral. Okay, so what's the first thing that you want to be integral, of course, is that the norm is going to be an integer. So you want the norm of alpha to be an integer. And let's just think about a good way to think about that norm, okay? So it's the determinant of some 2 by 2 matrix, M alpha. So suppose the eigenvalues of that M alpha are lambda 1 and lambda 2. And then the determinant of this M alpha, of course, is just the product of those two eigenvalues, lambda 1 times lambda 2. Okay, so that's great. Now, the thing is that, well, if alpha is an integer, well, surely if I add 1 to it, it's still an integer, right? So 1 plus alpha is an integer. That means that I want the norm of this also to be an integer. So you want the norm of 1 plus alpha to be an integer. But what is the norm of 1 plus alpha? And this now tells you why I wrote it the way I've done here, okay? Well, what are the new eigenvalues? The new eigenvalues are 1 plus lambda 1 and 1 plus lambda 2. And the product is now 1 plus lambda 1 plus lambda 2 plus lambda 1 lambda 2. Now, assuming that the first equation holds, okay, or this norm of alpha is in Z, that means that this product is in Z. 1, of course, is in Z. So really, you're saying that the sum of the eigenvalues here is also in Z. Okay, so that's a negative trace. So that means that the trace is also an integer. So not only do you want the determinant of this matrix to be an integer, you also want the trace to be an integer. Okay, and so what it looks like in this particular case is that, in fact, you want the entire characteristic polynomial of this M alpha, when you think of this as a F-linear map, you want this entire characteristic polynomial here. So the F here is actually Q. So let me just change that to Q. That's the bottom. That's the bottom field here, Q. You want that to be a integer with polynomial coefficients. Of course, it's a characteristic polynomial. So this is always going to be a monic polynomial. Okay, so that brings us to the definition. Hopefully that's sufficient motivation. You can, of course, carry out this thought experiment with fields which have a higher degree as well, and you'll come up with a similar conclusion. There's a little bit more work involved, but it's the same sort of idea, okay? So what is our definition? Okay, so suppose you have R as a subring of a commutative ring S, okay? So what does it mean for some alpha inside this bigger ring to be integral over the small one, to be integral over this R? And it just means that it satisfies some monic polynomial equation. So f of alpha is equal to 0 for some monic f whose coefficients are inside the smaller ring. So in this case here, the smaller ring was going to be z. Okay, but in this case here, we're working more generally with what's it meant to be integral over r as opposed to integral over z. Okay, So there's some natural additional definitions here. If you have some subset of S, when is it integral over R? If every element inside T is integral over R. And also, what happens if every element of S is integral over R? In that case, we say that this extension, extension of commutative rings, is an integral extension. Having introduced the notion of integrality, let's look at some important properties of integrality. And to do so, the best way is to introduce the following definition. Suppose you have two commutative rings, S and R, and this is an extension of commutative rings, so R is a subring of S. Okay, we'll say that this extension is finite if S is a finitely generated R module. Okay, so this is very similar to the idea of finite extension of fields. Okay, so let's look at the notion of integrality. If you have R is a subring of the commutative domain S, okay, so we have these three conditions and they're all equivalent. They're basically equivalent ways of defining integrality. Okay, so the first one is an alpha in the big ring S is integral over the small one. Okay, that condition is equivalent to the second one here. What you do is you look inside this subring and you look at the subring generated by R and this element alpha. So this is going to be a ring extension, commutative ring extension of R, and you want that to be finite. That's the second condition. The third condition is that rather than looking at R alpha over R, you have any finite extension of commutative rings, R prime over R, where alpha is inside R prime. And if you have this condition, this is also equivalent to the others. So let me tell you basically why this is true. Okay, it's not too difficult. So why does A imply B? We want to show that this is a finitely generated R module if alpha is integral over R. So alpha being integral over R means that it satisfies some monic polynomial, let's say this one here, with coefficients, these Ri's coefficients inside R. So what is this subring here? Basically you're looking at all polynomials in alpha with coefficients in R. And what this equation tells you is that whenever you have a power of alpha in that polynomial, which is alpha to the n or higher order, you can replace it with a linear combination of linear combination of powers of alpha, alpha 0, which is 1, up to alpha to the n minus 1. Okay, so you can keep using this, and eventually you'll see that, yeah, every polynomial in alpha with coefficients in R, you can rewrite as a polynomial in alpha of degree at most n minus 1 because of this equation. And so a finite generating set for this R module is 1 alpha up to alpha to the n minus 1. Now B, of course, immediately implies C because we can just take R prime to equal R alpha. So now to complete the equivalence, we just have to show that C implies A. I don't want to go through the full details, but the basic idea is very simple. And that's the following. So suppose R prime is generated by a finite number of elements, say A1 up to AM. And then what you can do is that since it's generated by a finite number of elements like this, what we're going to do is we need to find some monic polynomial that alpha satisfies. So where's that going to come from? Okay, so what we're going to do is we're going to try to represent this alpha. So alpha you can multiply by each of these generators, and it's going to be something inside this R prime. Okay, so alpha is inside this R prime. Okay, so you can write this as an R linear combination of these generators A1 up to AM. And as you do this, as you vary the I from 1 to M, okay, you'll get some M by M matrix. Okay, that's this matrix of Mij's, and that's the matrix M. And basically, this tells you what alpha does on generators, and if or left multiplication by alpha does. So it basically tells you what alpha does in general. Okay, so now we can use this M to study this left multiplication by alpha. And you know that this M satisfies the characteristic polynomial. Okay, so that's a monic polynomial. Okay, and since all of these entries are inside R, okay, the coefficients of this will be in R as well. Okay, so this M satisfies that. And if you look at this polynomial in this M, okay, what does it kind of represent? It just represents what that corresponding polynomial in alpha is doing on these generators, and basically you're saying it's 0, so if it's acting as 0 on all these generators, it acts as 0 on all of this, and hence it actually has to be 0 itself. Okay, so that's because this is well, I guess 1 is a linear combination of these, so if you multiply by 1, you'll get 0. Okay, so that's a basic idea of what's going on, and that's where you get your monic equation from. Okay, so that gives us a new way to think about integrality, okay, rather than looking at this equation here. Okay, so let's see how this is useful. So the first thing that's rather interesting about this is that suppose that alpha and beta are integral over R. We'll assume that there's some big ambient commutative ring extension S, which contains both alpha and beta. Okay, so we can add them together, alpha plus beta, or multiply them, alpha, beta. And you might think, well, are they integral? And the answer is, in fact, they are integral. Okay, so the sum of integral things is integral, and the product of integral things is integral. Okay, and in fact, we can say a little bit more. We can say, in fact, if you look at the whole commutative ring that's generated by R and these two elements, alpha and beta, that's going to be finite over R. Okay, and since that's finite over R, every element by this part C, every element inside here, any alpha inside R prime, is actually integral. So everything inside here is integral over R. So it's an integral extension too, okay, by definition of integral extension. And this, of course, contains things like alpha plus beta and alpha times beta. Okay, so that's the way you do it. And it's quite easy to see why this is finite, okay, so why is that? Okay, so alpha and beta, they're roots of monic polynomials, so we can write something like this for alpha, and a similar one for beta, okay? And let's suppose the degrees of those monic polynomials are D and E, okay? So what is this ring here? So this is basically all polynomials with coefficients in R in alpha and beta. So you look at monomials like this, alpha to the I, beta to the J, and you look at all possible R linear combinations of these. And just as we saw here, right, because alpha satisfies a monic polynomial of degree D, okay, if you see alpha to the D or any higher power, you can reduce it to a lower power and make sure that the only ones that you really need here are of the form alpha to the 0 up to alpha to the D minus 1, and similarly the only ones you need here are beta to the 0 up to beta to the E minus 1. So there are only a finite number of these monomials that you need to look at inside here. So that's a finite generating set as an R module. Okay, and that shows that this is finite, hence it's integral, and hence alpha plus beta and alpha beta are also integral if alpha and beta are. So that's a rather nice result, and it uses just this very, very useful proposition and a new way to think about integrality as well. Okay, so now we can come to our definition, which really tells you what can you think of as being the set of integers in some field extension, okay? So let R be a subring of a commutative domain S, okay? So if you look at the set of all alpha inside the big ring S, which are integral over R, then this is a subring of S. It's also a subring of S, by the way, that contains R, okay? So R, of course, is integral over R, okay? Because if you like, if you join alpha is already in R, then R alpha is just R. So R as an R module is, of course, finite, okay? So this will be something which is an extension of R, this set of all integral elements, and it's actually a subring, okay? And to check something's a subring, remember you just have to check closure axioms. And that basically follows here, like closure under sums, products and things like that, okay? So this subring of S is called the integral closure of R in S, okay? So now we can use this more fancy sort of a theory to revisit this notion of Gaussian integers. Why is this the correct sort of set of integers to look at in that sort of case? Okay, so let's look at this example. Okay, we're going to start with this degree 2 field extension of the rationals Qi, and you start with Z. That's a subring of that. Okay, and let's look at the integral closure of Z inside this Qi. Okay. Okay, so it should be kind of like a set of integers, okay, and it's a subring, and let's just see what it is, and I claim it's actually the Gaussian integers, okay, so this gives you this basic wonderful notion, gives us exactly what you want, okay, to recover this. And I won't go through the full proof why it's true, but let's just check slowly and convince ourselves that it ought to be the right answer, okay, and see how you can actually check that it is true. So let's first check that Zi is actually integral over Z. Okay, so all the elements here are integral. Okay, so what's the easiest way to check that? Well, Zi over Z is finite. As a Z module, this is Z plus Z times I. Okay, so it's finite, so in particular it's integral. So certainly this is contained inside the integral closure. And then the question is, do you have everything that is integral? So now, I guess what you do is you look at linear combinations of 1 and I, where you might have some denominators. Okay, and let me just show you how easy it is to show that they're not in there just by taking a particular example. You can do this in general, but I think if you've seen a particular example, it's quite easy to see what happens in general. Suppose, for example, alpha equals 1 plus I on 2, so this is not a Gaussian integer. Okay, so what you can do is you can say, well, if it were integral, it has to satisfy a monic polynomial, but actually, you know, it does satisfy some polynomial, and what is that? Okay, so the polynomial that it does satisfy is, because it is in a degree 2 extension, okay, is, well, you can look at alpha squared minus alpha. So alpha is basically the negative real part, okay, and then the modulus squared is half, so it satisfies alpha squared minus alpha plus half equals 0. Okay, so if that's the equation that it satisfies, it's not going to satisfy an integral, monic integral equation, okay, because the set of all polynomials that it's for which this is 0 of is just multiples of this. Okay, so that's how we generalize the notion of norms that we see in Gauss's study of sums of squares, and also the notion of integers. I hope you enjoyed this adventure in pure mathematics.